Hi, hello, welcome to my channel Chem Cloud. Let's learn chemistry. So here in this video, we are going to discuss some part of spectroscopy for organic chemistry. So specifically here we will discuss structure determination from spectral data. So firstly we will cover all spectral problems and then we will start with the theory. So let's start. So here we have our problem number one. Just read the problem with me. Reduce the structure of compound based on given spectral data. So there is one colorless liquid with molecular formula C4H8O. IR value is given as 1715 centimeter inverse. H1 NMR values. So three peaks are given, right? So we'll write preliminary observations first. So in H1 NMR there are three peaks, means there are three groups of equivalent protons, right? So these three groups are 3H, 3H and 2H. 3H, 3H and 2H. So we have peaks for all 8 protons. Then in IR we have value for 1715, which indicates presence of carbonyl group, and in molecular formula there is one heteroatom which is oxygen, right? So this is our preliminary observation regarding this spectral data. So we'll start with the details of this. So molecular formula is C4H8O. So from molecular formula we will find out sites of unsaturation. So this is also called as double bond equivalence or number of hydrogen deficiency. So what will we do here? We will compare this given formula with formula of saturated hydrocarbon. So for saturated hydrocarbon, general formula is CnH2n plus 2. So if there are 4 carbons, so for 4 carbons it must contain 4 into 2 is equal to 8, 8 plus 2 is equal to 10. So for 4 carbons it must contain 10 hydrogens. Now you compare this with given formula. So here we have only 8 hydrogens. So there is deficiency of 2 hydrogens. So in case of site of unsaturation, so that deficiency of hydrogen divided by 2 will give you site of unsaturation. So in this case site of unsaturation is 1. So this is the first problem. We will go in little details of this. So suppose this is one compound given. So it's N-butane C4H10. Right. So from this C4H10 we will remove two hydrogen. This hydrogen and this hydrogen. So after minus H2, what we will get is we will get one double bond in this compound. So compared to saturated hydrocarbon, there is deficiency of two hydrogens. So this deficiency of two hydrogen is correspond to one site of unsaturation, which is double bond, right? Similarly, we'll remove this hydrogen from this terminal carbons. So when we remove the hydrogens from terminal carbons, right, so we'll get cyclic compound. So here also, like two hydrogens less compared to formula for saturated hydrocarbons. So this deficiency of two hydrogen or one site of unsaturation is correspond to presence of a ring or cyclic structure, right? Presence of one ring. So one site of unsaturation indicate presence of either one double bond or one ring in the structure. Okay. Now in IR we have given 1715 centimeter inverse, right? So in case of IR, so if it is ketone, it will be 1715 centimeter inverse. If it is aldehyde, it will be 1725 centimeter inverse. If it is carboxylic acid, the value for CO stretching will be 1710 centimeter inverse, and if it is ester, then value for CO stretching will be 1735 centimeter inverse. So now in molecular formula there is only one oxygen, so we are not going with the possibility of carboxylic acids or ester. It can be either ketone or aldehyde. So we are not going with the possibility of aldehyde because there is no peak for this aldehydic H in H1 NMR, right? And the value for this aldehyde is 1725. So if it is lower, this must be conjugated. but we have only one site of unsaturation, right? So there is no possibility of aldehyde, so it must be ketone. It must be ketone. So this 17, 20, 15 corresponds to CO stretching of ketone. And in H1 NMR, if you see, we have three groups, right? 3H, 3H and 2H. So these groups must be CH3, CH3 and CH2, because in molecular formula we have only 4 carbons. One carbon we have used to form carbonyl group of ketone. So this, with the remaining 3 carbons and these hydrogens, we can form these 3 groups, CH3, CH3 and CH2. The second observation, this J value for peak A and peak C are same, means this A and C must be connected to each other. So this triplet of peak A must be because of these 2 hydrogen in peak C, and this quartet of peak C must be because of these 3 hydrogens in peak A, right? So this CH2 and the CH3 must be connected to each other, right? So we'll write this. Now you observe chemical shift value. So chemical shift value for this peak B is 2.14. Chemical shift value for this is 2.43. So this CH3 must be connected with carbonyl. This CH2 must be connected with carbonyl, right? So what we have is, we have this CH3 for singlet, then we have carbonyl group, and then we have this fragment of CH2 connected to CH3. So this CH3 is connected to carbonyl group, this CH2 is also connected to carbonyl group. So this compound must be this, right? So this is your 2.14 3H singlet. This is your 2.43 2H quartet. Then this is your 1.19 3H triplet, and this carbonyl is showing 1715 centimeter inverse, right? So you can write this data for each group. So this is the answer for first problem, right? Now let's move to the second one. So here molecular formula is C9H10O2. So there are two hetero atoms which are oxygen, two oxygen atoms are present. Then IR is recorded with a KBr, so it must be solid compound. 1720, so it must contain carbonyl. Then we have this 1602 and 1581, so these are for C double bond C of aromatic, so it may contain aromatic ring. Then we have this 1270 and 1105, these are for ether. And this 750 and 690, these indicates the presence of monosubstituted benzene, so it may contain monosubstituted benzene, right? Now go to H1 NMR values. So there are 4 groups given, 4 peaks given. So if you observe chemical shift value 1.29 and 4.35, these are aliphatic protons, and this 7.4 and 8.8, these are aromatic protons, right? So this is a preliminary observation we have written. Now we'll start with the detailed analysis of this. So from molecular formula, we'll calculate sites of unsaturation. So we'll compare with formula of saturated compound. So for C9, there must be 9 into 2 18 plus 2 20 hydrogens, right? There must be 20 hydrogens. So if you compare with this, there is a deficiency of 20 minus 10 hydrogens. There is deficiency of 10 hydrogens. So site of unsaturation is equal to 10 divided by 2, 5, right? So this site of unsaturation is 5. So whenever your site of unsaturation is more than 4, it may contain benzene ring. So if you consider benzene ring, we have 3 double bonds and 1 ring structure. So for 1 benzene ring, site of unsaturation will be 4. So now we have site of unsaturation 5. So our compound may contain 1 benzene ring and 1 more some double bond or ring, right? 1 site of unsaturation we need to check. Now we go for IR. In IR, it is given as a 1720. So we have discussed in last problem, if it is ketone, it must be 1715 centimeter inverse. If it is aldehyde, it must be 1725 centimeter inverse, and if it is ester, it must be 1735 centimeter inverse, right? So now this compound is 1720, showing fundamental vibration at 1720. So it may be aldehyde or ketone, or it may be conjugated ester. So because of conjugation, this 1735 value will drop, so it may appear at 1720. So there's three possibilities: it can be ketone, aldehyde, or conjugated ester. These two peaks which are given and around 1600, 1602 and 1581, these are C double bond C stretching of aromatic ring, right? If it is aliphatic, it will appear near 1650. And then this two, 1270 and 1105, these are COC ether linkages. So these are stretching vibrations of COC bond, right? So symmetric and asymmetric stretching. And then we have this 750 and 690, these are out of plane bending vibrations, out of plane bending vibrations of CH of benzene, CH of benzene, right? So these vibrations indicates, this 750 and 690 indicates presence of monosubstituted benzene, right? Now we'll go for next H1 NMR. So in H1 NMR, first we will see this C and D, which are aromatic. So in aromatic we have peak for 5 protons, 3H and 2H. So it must be monosubstituted benzene, right? So we have H, these are ortho protons, right? So this is 7.403H, multiplied this for these protons at ortho and para position, and this 8.812H multiplied, this is for these protons on the meta position with respect to this substituent. So just suppose there is X as a substituent, so substituent X we need to find out. Now you go for this. So what we have here, we have 3H triplet, J is equal to 8 hertz, 2H quartet, J is equal to 8 hertz. So these same J values, so these must be connected with each other. So we can simply go with the CH3 CH2 group. So because of this CH3 group, we'll get a quartet for this CH2, and because of this CH2, we'll get triplet for this CH3. Now you can observe the chemical shift value is 4.35 for this 2H. So this must be attached to oxygen. It must be attached to oxygen. So if it is attached to oxygen, the value may appear close to 4, right? Now see what are the fragments we have. We have one benzene which is monosubstituted, we have one carbonyl, and we have O CH2 CH3 group, right? So just need to connect them, so we'll get this ester, ethyl benzoate, right? So you can write these frequencies there. This carbonyl is conjugated, CO is conjugated, so value will be 1720 centimeter inverse, right? These values of H1 NMR and these values of aromatic peaks we can write here. So this is the answer for this second problem, right? So like this we will take number of problems and we will try to solve or cover all type of spectral problems, right? Thank you so much.